So I'm going to be talking about the project, a little bit of background on the project, why we chose HSDS, and then hopefully spend the bulk of the time talking about suggestions for future HSDS development. So SlideRule is a project funded by ISAT2, really to make their data more available. They produce a lot of low-level data, about 150 terabytes a year, depending on how you classify low-level. It could be more than that if you include a little bit more. And just to put it in perspective, if someone wants to analyze just a year of the data and they're egressing at 100 megabits per second, it's going to take about 4.5 months just to download that data set as it exists right now in NASA DAX. If you're lucky, you're in a part of an institution that has internet 2 access. Does everyone hear that feedback? I'm hearing a bunch of feedback. Yeah.
We can see.
Okay. So if you're in an institution that has internet 2 access and you're pulling it at 400 megabits per second, it's still going to take about 5 weeks just to download just 1 year of the lower level data. And so really what that means that unless you're in one of these big institutions and you have access to a supercomputer facility, something like that, the low level data products are really inaccessible to you. NASA's solution to that right now is that we provide some select higher level data products that are much smaller, that target certain science communities. So then the problem becomes, is your science community targeted by one of those higher level data sets? And if it's not, and you're forced to use the lower level data sets, that's the problem that SlideRule is trying to address. So a quick overview of the architecture of SlideRule. It's a server-side code written in C++ and Lua, and the idea is that it provides these REST APIs for processing science data on demand. So the scientists can hit our service and make processing requests with parameters that are suited to their research, and then our servers will hit the bulk lower level data products that the ISAT2 has and just return the higher level products back to the researchers. And so to provide the backend data service, we chose HSDS. And we're running in AWS, so the data is in S3, HSDS is running in EC2, and we're running in EC2. And then the communities that we're targeting first are the snow depth mapping and glacier research, both of which the higher level products aren't optimized for currently. So why did we choose HSDS? Well, so what do you do? So you have a big processing pipeline on the ground that takes hundreds of terabytes of data and process it to these higher level data products, and we want to parameterize that. And so one idea could be we just take the whole operation and we move it over to the cloud. So why doesn't that work? The reason that doesn't work is because it just costs too much. To duplicate the same infrastructure that you have locally in the cloud, while it will work, you're losing all the cost benefits of moving to the cloud. And so I just put down I looked it up, just hosting 150 terabytes on an NFS-like file system in AWS is $45,000 a month. So just to even create that part of it becomes cost prohibitive. And then when you go to use the things that are cost effective, you find that that your architecture has to change. So the access to a local file system, things that are efficient accessing local files, they're not efficient when you're accessing the same data in S3. So then the next part is, well, okay, well maybe then you just transform the data into a cloud optimized format, right? And we went down that path as well, and we looked at different formats that are from the ground up optimized for the cloud, optimized for being stored in S3. The problem then becomes, well, we've had years of investment in HDF5, and all of our data is in H5. There's a lot of internal tooling that we have with H5 that works very well that we want to keep. And we have partners that have developed third-party tools that work with the H5 format. And so if we change the format to optimize for cloud, we're really turning a back on all of the work that they've done. And so then that gets us to what we chose. So we said, okay, so HSDS fit perfectly. We were very excited actually to find this offering from the HDF group. So the idea here is that, yeah, you get to keep your format and you get to have cloud optimized access. And John's presentation on that says why. But then I just want to point out that we took it a step further. So we're using HSDS as a backend, and we are able to keep all of our existing tooling in our server code. But one of the nice benefits that we found is that power users don't, when we run HSDS, we don't have to go through our servers at all. So we can provide that on-demand processing engine, and we can make that accessible to people that are remote or people that don't want to deal with the complexities of handling the bulk lower level data products. But for scientists that are familiar with the data products, well, they can run their code and directly access those as well. It becomes another access point, another API. And you can even take it further and say, well, those institutions could then co-locate in US West 2. And now they're having the same code. They can hit our APIs, or they can hit HSDS, and they can leverage all the benefits of AWS. So this really was a good fit for us. It was a perfect fit for us. So for the sake of time, I'm just going to jump forward to suggestions for future HSDS development. We've benefited a lot from working with John over the past couple months, and we appreciate the support that we've gotten. And this is kind of late breaking. And so I figured this would be a good time to share where we're at. It is not, this is still early on, but so I'm hoping that maybe this will spawn some thought, some future investigation. So what we are finding is when you do a native ingest into HSDS, it takes your H5 file and it breaks it up into into the optimal size chunks for being stored in the cloud. And so if you take an H5 file and you just ingest it through HSDS and you access it through HSDS, we saw very little degradation in performance. Now there is an option though to do it instead of ingesting it through HSDS, to store that file off to the side in its original format and have HSDS just point to it. And we call that the link option. And the reason that we are very interested in doing it this way is that we don't want to pay for the cost of hosting all of the ISAT2 data. So NASA is going to do that anyway. And so we want to leverage the benefit of that. And I think that we're not unique in that large institutions are often going to host their data and bear the cost of that. But smaller groups like ourselves want to be able to get access to that data while just paying for compute. And the link option is what provides that. The problem is, though, that when we went to the link option, the size of the chunk inside the H5 file became extremely important. So what do I mean? So here is a little bit of an eye chart, but bear with me. So the table at the top is listing all of the data sets that we read out of one H5 file that ISAT2 produces. So this is ISAT2's lower level data products. and we read you know, a dozen or so data sets. Actually, there's some parameters in there, so I think it's about 70 some data sets that we read out of one file in order to produce a higher level product. And so we started looking at the performance of each of these reads through HSDS, and it was taking forever. But then when we drilled down, we saw that most of the data sets were actually performing fine. Like, there was no issue there. It was only a couple. There was only 3 data sets that were taking the overwhelming portion of the time to read. And so you can see those 3 outliers, and we plotted the duration on the y-axis for on the left here to the average chunk size, and on the right the number of chunks. And in both cases, you see that these 3 data sets, in which there are 11,000 chunks in the current ISAT2 data per data set, it just overwhelmed the performance. That's where everything was. And so now, going to this next chart, so we did some further tests, and we started looking at different parameters. So we said, okay, let's just read the file locally. And this was all on C5 X large. That's a 4-core, 8 GB system. It's got up to 10 gigabits of network, so we're not going to be network bound. So we read locally, and it took 10 seconds to read the file. Okay, so that's our baseline. We did the native ingest, and it took 60 seconds, which is fine for us because we're happy scaling, you know, paying for a little bit of performance, upfront performance with the ability to scale, because we can scale to 100 nodes and easily drive down that duration. But when we went to the link option, we saw an order of magnitude jump. And so we saw runs between 990 seconds to 1,000 or so seconds. And that really becomes a cost breaking point. So now we can't scale to that level without really facing insurmountable costs in EC2. So we did some other things. So we looked at compression. Compression really doesn't make a difference. It's not helping, hurting. We scaled, we ran more data nodes on the C5 instance, didn't really help. We bumped up to a 16-core C5 instance with 32 gigs of RAM and ran 16 data nodes. It helped a little bit, but it wasn't linear. And so then talking with John and getting his help, you know, he was the one that pointed us out to the sensitivity to the chunk size. So we said, okay, well, let's use the H5 repack and just make every data set 1 chunk. So a data set is 1 chunk. In fact, we're using the continuous option with compression, and like that, it came down to 30 seconds. So it's actually beat the native ingest by a factor of 2. And it's the same data, right? So we're still pushing 718 megabytes across the wire in every one of these instances. And through chunk size, we have this range between 30 seconds and 1,000 seconds. A huge sensitivity to that. So the thing that we realized is that when I've been using H5, I think it's been on three missions now, chunking sometimes mattered. I think for most of the cases, I didn't really pay any attention to it at all. And I just put some words in here for people to read afterwards if they're looking at these charts as to, you know, when it matters, when it doesn't matter. Everyone has their own case. But the take home for us right now is that when using HSDS, I think chunking always matters. You have to be aware of it, because the cost going out to S3, that connection, you're going to pay for it one way or the other. If you are making them too big and you only want to read a little bit of the data, well, you're going to pay for the overhead of moving that whole chunk down just to pull out the little bit. And if you make it too small, the overhead and the individual connections to S3 are going to overwhelm your throughput. And so, so that is the big aha for us. And there's a lot of work to do, right? So we're still in the process of trying to figure out where the bottlenecks are. You know, is things bottlenecking S3 because it's all hitting the same object? Are we choosing the right number of data nodes, service nodes, things like that. And you can see, there's a lot of different dimensions: size of the chunk, size of the data set, compression, caching, not caching, things like that. And so the holy grail, I think HSDS is something that's allowed us to have our cake and eat it too, in a little bit. Like we got to use all of our existing tooling and have cloud optimized. And then I think the next step is to, can we have our cake, eat it too, and have the icing on top, and that would be, is there a way, can we be clever? Can we brainstorm and think of ways to have the linked option work without having the user have to worry about the chunk size? Is there some clever things that we can do there? And I think that's really our big suggestion for the HDF group, something that we would love to see. Okay, that is my last chart. Thank you, guys.
Thank you so much. There is one question in the chat asking, how do you know the number of chunks read by the library to complete a request?
I think we used HDF5 and looked at the number of chunks, in the chunk size, number of elements in a chunk versus the full number of elements in the data set. So it was a little bit of a manual process up front to use HDF5 to get that data, but it was well worth it to see what was really happening.
Okay, any other questions?
I have one. I'm Alexander Jelinek from HDF Group. So are you aware of the NASA trade study that HDF Group did maybe 2.5 years ago with OpenDep regarding cloud access to to NASA HDF data? Because a lot of these things about chunks and when to pull a whole thing versus the chunks, we talked about that trade study. Where we used OpenDep server rather than HSDS, but essentially it's the same problem. It was funded by Hsds.
Trade study. I know that there's been some OpenDAP discussions internal to Goddard, but I don't know if that's a study that's openly available. If you can distribute,
yes,
I'd love to read it.
It is a published NASA technical report.
Oh, that'd be great. Yeah, if there's a way to provide in the chat or in Slack, maybe a link to that would be great. I'd love to read it.
Because again, those kind of things, when to pull just pieces of a HDF5 dataset versus the whole thing, or even versus download the whole file, rather than just going access. That was all kind of analyzed through various use cases, because as you say, in the object access, getting 10 times, 100 times more data is sometimes worthy than having 10 small requests for something.
Yeah, that'd be great. Thank you.
No problem, thanks.
Cool.